Dear students, in today's lecture we will discuss about introduction to single phase induction motors and starting of single phase induction motors. First of all, introduction to single phase induction motors. The diagram shows that there is a single phase induction motor. So there are only two poles, one north and one south, and in this case the stator and rotor are aligned to each other with opposite poles attracting towards the other's end. So we discuss some points about this. The magnetic field in a single phase induction motor does not rotate. The main point is that there is no rotation in the magnetic field in a single phase induction motor. No starting torque. Since there is no movement, so there will not be any torque. No relative motion between the stator field and the bars of the rotor. So it's quite obvious that there would not be any relative motion between stator field and bars of the rotor. No induced voltage due to relative motion in the rotor. Since there is no relative motion, so no induced voltage. Voltage is induced in the rotor by transformer action. It will act as a transformer where the secondary winding is short circuited. At stall conditions, stall means stop, at pause or stop, at stall conditions or stationary. At stationary conditions, the motor looks like a transformer with a short circuited secondary winding. Current flows in the rotor. Rotor magnetic field lined up with the stator magnetic field and no net torque produced. Why no net torque produced? Because it can be seen that BR and BS are apart from each other with 180 degree. If we put 180 degree in the formula of torque induced, then BR cross BS and BR BS sine gamma, and this would be BR BS sine 180 degree, which is sine 180 degree is equal to 0, and it would be 0. So there would be no torque induced. Once the rotor begins to turn, an induced torque is produced. Why a torque is produced in the rotor once it is turning can be explained by two basic theories. First theory is the double revolving field theory of single phase induction motors, and the second theory is the cross field theory of single phase induction motors. We will discuss the first theory in this lecture, and second is left for you to read from the book. The double revolving field theory of single phase induction motors. In this case, as shown from the name, that this is double revolving field, so it would be double revolving field Starting from here, you can see that two fields, revolving fields, B clockwise CW and B counterclockwise CCW. So the direction of motion is apart from each other. Their magnitude is equal to each other, but they are moving in opposite directions. So BCW and BCCW. If we see at this point, again this is BCCW, BCW and moving away. At this point, this they are 180 degree from each other, and there would not be any torque induced, and BS is also 0 in this case. Similarly, this is again BCC, B counterclockwise and clockwise. In this case they are aligned, in this case they are apart by 180 degree again, and BS is 0 again in this case. Now it can be seen that both the fields are in opposite direction, moving in opposite direction, but with same magnitude. Then we know that torque on y-axis and speed on x-axis. So the graph would be showing the torque speed characteristics. In this first diagram, this is a simple torque speed characteristics of the motor, but in second diagram we have two dotted diagrams which are opposite to each other, and in between is the net of these both torques, and this net is basically the addition of these two dotted lines. Like at this point, this is, let's suppose, plus something, and this is minus exactly same value, same magnitude. So plus minus cancelled and the net value is 0. Similarly, this bold line is showing the net value. Starting single phase induction motors. Now we come to another topic which deals with starting single phase induction motors. No intrinsic starting torque. There are three techniques commonly used to start these motors. Single phase induction motors are classified according to the methods used to produce their starting torque. So these are the three methods to start the motor. First one is split phase windings, then we have capacitor type windings and shaded stator poles. Split phase windings. In this case we have a diagram where we have main winding and we have auxiliary winding 90 degree apart from each other, as can be seen from here. In this case, the ratio of R over X for auxiliary winding is greater than that ratio for main winding. Then there is a centrifugal switch and this switch will be on or close to complete the circuit. Since the ratio for auxiliary winding for R over X is greater from the ratio of main winding, so current of auxiliary winding would be ahead from the current from main winding. It can be seen from this diagram quite closely. Similarly, if we want to see the torque induced and speed on x-axis, the ratio between torque and speed, then this would be main plus starting winding. This bold line is showing. This is only main winding torque because of only main winding, and this would be a centrifugal switch. Now we come to another type of windings which are used to start an induction motor. So this type is capacitor type winding, which is further divided into capacitor start motors, permanent split capacitor motors, capacitor start, capacitor run motors. Capacitor start motors, we have capacitor on the starting switch. So in this case, if we see the main and auxiliary winding has a torque, and then we have a switch, capacitor start switch which is connected with capacitor, and then if we consider the only main winding, this would be something like this. So this will be the complete diagram, which is around crossing around 400%. Now the permanent split capacitor, this is a capacitor which is permanently connected over here. In this case, the diagram is quite flat than the previous case, simpler since the starting switch is not needed. At normal loads, they are more efficient and have a higher power factor and a smoother torque, this is quite smooth, than ordinary single phase induction motors than the previous case. Lower starting torque than capacitor start motors. So the starting torque is also quite low than the capacitor start motors. Now we come to another type which is showing capacitor start and capacitor run. So this is capacitor start connected with starting switch, and this capacitor is called capacitor start, and this capacitor which is connected in shunt with the circuit is called capacitor run, and this capacitor start and capacitor run would be used to start the induction motor in some specific cases. In this case, the torque and speed characteristics can be represented like this, where starting and running capacitors are going through almost 300% torque, and then there's a switch, and then we have these are the running capacitors. Thank you.